So let's get started. Today we're very lucky at the end of the semester to have well, the best for the last maybe speaker we have here in terms of the topics and the quality that you will hear in this presentation directly, of course, overlapping my research field. And over the years we have shared and we have worked together a lot. It's my distinct pleasure to introduce Professor Anand Pupala from University of Texas at Arlington to come here and give us his opinions and research experiences on transportation geotechnics in general. I know he's been working more on transport payment aspects, but I think we're now hoping to do some rail work too in the future. And also in the ISSMG, we're working together on separate committees, but under the umbrella of the Soil Mechanics and Geotechnical Engineering Organization, ISSMG, as well as I know him for years. He did his PhD work at Louisiana State University, and he had, I told one, but actually he had two Turkish professors there who are very close to me. So we go way back in many different ways of connecting together, okay? And then at TRB the same way. I know he's a section chair of a related committee that I'm a chair of the Geology and Earth Materials, and he's with Soil Mechanics section. And what else? Let's see. He wants me to cut it short. I mean, sufficient to say that he's already having centers on sustainability and transportation geotechnics. And well, without further ado, I guess I should let him talk to you and talk about his research on expansive soils, soil stabilization. I'm looking at my class people, and they haven't showed, well, except for one person.
Okay.
But we are recording this great presentation. So.
Thank you, Errol. Thank you. Thanks for inviting us. Really a great honor for me to come and give a talk here. I think one thing is I want to mention is the way my topics I'm going to present here all has something related to pavement or geotechniques, but I'm going to go from bottom up. That means we'll talk with the expansive soil, which is your natural subgrade, then we'll talk about stabilization, and then I'll talk about a couple of projects where we're bringing a lot of sustainability information, and that's a pretty big thing from DOT perspective. So with that, let me go to my next slide here. So this is how we're going to have a little bit of introduction. And then talk about expansive soil. I think many of you probably know that Texas is well known for expansive soil problems. I'll show you some, if you don't believe me, I'll show you some pictures that will really convince you that we are a really problematic soil area. And in my opinion, that's the reason why we get a lot of research also. So the number 3 topic is stabilization. And we want to go away from the empirical design. Yes, we still do empirical design. I'm pretty sure a lot of DOTs still follow the PI-based design. And I will try to convince you that that's probably not the best approach, because we spend more time in doing forensic work than doing initial investigations. That's where I'm going to bring clay mineralogy information, and then 2 case studies, and then I have some closing remarks. So I think, the biggest problem actually, I was looking at the expansive soil damage. How much is this going to be is typically. I think, some of the recent estimates are $15 billion. I'm talking about infrastructure, including homes, roads, all kinds of industrial buildings and parking lots. If you add up all these things per year, is around $15+ billion damage. And a lot of times, if you look at the map, I'll show you in a minute, in the U.S., it's not just confined to Texas. It actually has everywhere. And there are areas that are, we are learning more. So there's a problem with that expansive soil. So it's an important thing is whenever you put a structure, we have to really do a better characterization. So I'll talk about this one a little bit later. And then when you have a problem soil, obviously you have to stabilize them before you put the structure. So let me show you some pictures where, the expansive soils are located. It was like a kind of a joke at some time, if these expansive soils are in this area, the amount of research on expansive soil is probably 4 times than what we are doing right now, or 5 times. If you look at it, all these bad soils are here. It's all Dakotas. If we have a more dense population over there, this would have been probably the, NSF and others. They still invest research, but still the amount of research they're investing is a lot less. So it was something, but if you look at it, Colorado has them, and then California has pretty significant amounts of expansive soil. And in the southeast, pretty much most states have the expansive soils. And we work with, in this region, particularly Oklahoma and this part. And again, as I said, this area, not that bad. They have other soil problems like soft soil, but expansive soil is not a major issue. And I think the very common thing is they really swell and shrink. And this is the shrinkage what you get typically when you have a dry summer, which we are very well known in Texas, so we have cracking. The first rain that hits, water is going to go much deeper. And then you have soils that's going to really start swelling. And these soils are not everywhere uniform. So areas where you have high amount of smectite soils, you're going to have a heaving. So almost every area we have a kind of a roller coaster rides. In fact, if you drive in the Dallas region, I can give you a couple of them. Probably the amount of roughness you can calculate there is going to beat you completely away. I think Carrollton, he knows. 635. So see, I don't have to. This is very easy for me. He's from Dallas, so he can tell you. If you don't have to believe, it's pretty bad. There's one particular reason. They tried 2 or 3 times different stabilizations. Every second year, they had to go back and repair. So it's a big maintenance for the DOT and also local cities, because a lot of local roads come from that region there. And this one is from Middle East, but it's a kind of common. Like in Dallas also, we have a lot of cracks in our homes. In fact, there was a statistic I'm going to throw at you right now. In Dallas, if you look at the phone book on the yellow pages, you don't have the phone books anymore, but still, if you look at the yellow pages somewhere, you'll find there are 60 plus repair companies in Dallas. And you go to New York City, you only have 2 or 3 people. So it will tell you how big a problem. The biggest problem in Dallas is this foundation companies, they only have the company for 2 days, 2 years, and then they say bankrupt, and then they go away. You won't even find. So the guy who fixes your home, next year you want to go back because you have the problem came back, you can't even find him. He'll start with a new company again. So basically it's a big industry there. All this cracking, and anytime you have a crack, you lose like 20% of the value of the home sometimes. So it's a major issue. And we deal with quite a bit of these home issues. And we also have the retaining wall. Sometimes the backfill is still expansive soil. If you have a cut area, you have a retaining wall that starts moving. And I'll show you a picture, and I'll explain you how big is this problem. And this is all from our region. And I actually call them expensive soils, because anything you build, they're very expensive because of high maintenance. This particular one is an I-30 outside Dallas. When this wall started moving due to this rain in the backfill, and then started swelling, and the wall only can move in this way, so this interstate started buckling. And they had to shut down the whole system for at least a month or more than a month. Imagine one lane being shut down. You can see those, all the markings over there. This kept the traffic in the mornings for long lanes, and amount of man hours lost is unbelievable. And this is common in our area. We have heavings like this everywhere. And this is the area where I do quite a bit of research now also, the embankments or dams. First time when we get the rain, we have a lot of these superficial slope failures. And these are massive. These are not small ones. They actually take huge amount of soil and then comes down. And a lot of times they go back and push the soil. That's the only thing. It costs like $30,000, $40,000 to push back. In 2 years, again, they come back. And, a lot of earth dams, if you look at U.S. Army Corps, almost every year they have like 5 to 6 slides per dam in certain areas, and it's the ones that when you have a bad summer, you expect this problem pretty bad. And then this is again foundation crack. This particular building is a pretty new building. Within like a year, they have the cracking. So the damages from the pavement point of view, there are 2 types. The first one is, again, I just mentioned about you have the roller coaster rides coming differential heaving. Some area goes up, some area drops, so you have a differential heaving. The other one is this one, longitudinal cracking. This picture, I took this for my project from TechStart. It's a Paris, not this nice Paris, but we have another Paris, I think my friend knows. And this Paris is pretty nice, but this road is actually 4 or 5 months old. You look at the cracking here. We're talking about 2 inches wide, and we measured it just by poking a kind of a pole. We went up to almost 1.5 feet. I'm pretty positive it went much deeper. This was during summer, extreme summer, probably sometime in July. We took this thing. And all along this is the trees. The water is dried up and took away. The whole soil is cracking like from the bottom up and started going up all the way. And this one, they had to repair this thing they spent quite a big amount here from that regional district to repair this road. And it's a pretty new road. It's not like something, and it's a very common phenomena here, having cracking coming from the bottom to the top. So we were looking for solutions that are sustainable, that will provide something. We can show that, if we provide a little bit upfront cost, this is something always a challenging role. Can we try something new technique, a new material? Can we show you that the life cycle benefits are good, but more importantly, your maintenance dollars are less? So that's what we're trying to do. And I'm very fortunate. TechStart has a good sustainability group. So everything that we do, they look for sustainable metrics. So that's where we actually address it. In the case of civil engineering, if you want to know what is sustainability, these two fields we can directly identify. Dams, energy structures, you can easily tell. But in terms of pavement geotechnics, it was a little bit difficult for us to explain what it is. But we are learning as we speak. And I was looking at the pictures behind there. You have the air pollution, NOx, and different things. This is something I worked with air pollution group to tell me, like every time I have a traffic, a road bad, and then you shut down the road one lane, how much of the traffic air pollution, how many cars are idling, how many big trucks. I can calculate them and I can show a number, quantify how much pollution that's going to generate. They'll understand it. And actually it's helping me now to get projects. So it's something you guys have to learn as we speak, and I think you probably know some of you. I think this is where I think pavement geotechniques, we need to show that benefits, and then we can get more projects. So the second item I'm going to start showing you is, this is one of the first one, it's actually expansive soil underground. And this is a project we did. We looked at the expansive soils. How do you know a soil is expansive? They look at the PI. They say high PI, soil is expansive. But I can show you some soils that are high PI that don't swell. So the PI-based characterization is really misleading. You can't just use the PI always to indicate it, because PI can go, soft materials also can have high PI. So what we did is we wanted to go a little bit more fundamental type of thing. So NSF is the right place. So we just completed last year this project. So we'll try to include unsaturated soils properties, which is soil water characteristic. It's a study we did it, and actually I show you some results here. So basically, instead of identifying simplistic, like, okay, only use PI and tell me soil, if I give them much more fundamental, even though it requires additional testing, it will be much more sound. So when I design a structure, I'm doing a couple of additional checks above PI. That will help them much more than just using PI. So what we did is, in this study, we looked at the clay mineralogy, we looked at unsaturated soils. These things are already included. Pore size also we tried, and I'll show you a little bit information on that. So when we developed our swell models for expansive soils using these, which is beyond the PI, so it actually helps them better understanding of the soil behavior than simplifying it. So what we did for this project, we took 8 soils. We tried to get it from different regions, as you can see here. These are some of the soils we collected and in our research. Most of them are high plasticity clay. That means they have high PI. So we looked at them, and what we did is each soil we compacted and studied swell properties. Not going to go into swell testing, but basically swell properties are mostly swell strains and swell pressures. And then we studied SWRC, which is soil water retention curve. If MEPDZ has that soil water characteristic curve built, so we use that. And this is where we actually came up with some contribution to this field, clay mineralogy. Clay mineralogy I can qualitatively identify by doing XRD, but we came up with a procedure. Actually, it's a Jim Mitchell's procedure. Jim Mitchell has done in soil behavior book, clay mineralogy. Most clays have dominant clay minerals, are 3 of them: illite, kaolinite, and montmorillonite. And we try to do 3 chemical measurements in the lab on the soil to identify these 3 minerals, and that will add more to your soil behavior. It will tell you if you have a high montmorillonite, it's highly expansive. You don't have to do PI anymore. So this is where we added. Then we also looked at the pore distribution, because moisture migration in the soil is a function of how pores are connected. So, and that's again function of your compaction conditions. So we looked at all of them, and then we developed some prediction models. And I'll show you, these are more robust than what you do with the PI. So this is your SWRC curve, soil water retention curve. So basically, this side suction is 0. That means soil is fully saturated. So you are high moisture content, a volumetric or a gravimetric moisture content here. As you dry, desorption, you come to an area where it's almost very dry, so pretty high dry. In our subgrades, sometimes in Texas, we go around 10,000 kilopascal, which is very high dry condition. And that is when it starts cracking, and then all kinds of distress starts developing to the top. So we use this as one of the characteristic curve. And the first model, what we did is we looked at this soil as a water characteristic curve. We got these numbers. and then we know the swelling, so we calculated moisture. So we took the slope of the curve. So these are some of the 8 soils we tested. We didn't try to look at the dry path or wet path. We only looked at starting point and end point. I understand in between the slope is not linear, but we tried to simplify it. We just took a simple slope and a logarithmic plot. So we got the slope comes from alpha parameter, which is similar to your consolidation. And then we looked at the other model, C is clay. Every soil has a different clay mineralogy. So we looked at the clay mineralogy index and we came up with a parameter called C. And we multiplied these two, come up with a parameter called mechanical hydrochemical model. This is a little bit complicated, but it's not that complicated in our opinion. It just measures clay mineralogy. It gives you better understanding of your swell potential. So when we calculated, we compared them with our swell properties. This is the x-axis, our parameter we measure for each soil. This is swell strength. And you can see there's a nice trend how they are moving. So I can use this better than using PI. If I use PIs, I can actually easily underestimate or overestimate my swell potential. Whereas with this one, which is more fundamental because it accounts for your mechanical parameters, it accounts for hydro because your soil is unsaturated, it swells, and then it accounts for chemicals, which means your swelling minerals. So it includes all the three, and these are all three are multiplied because they're like product type of distribution. They have a kind of a not a cumulative but product type of influence on each parameter. So it came up very nicely, and we published this research on the topic here, and we showed both swelling and vertical swelling. We can predict very nicely with this, and it was a better model than us, and then we further calibrated later. The next model we did is when you have a good graduate student, you want to get more papers out of them, right? So what we do is we try to ask him to do a little bit more additional work, and this is where we did is identified already all 3 clay minerals, and you can see here each mineral has a different thickness. Okay, in the case of Montmorillonite is known as the worst swelling clay. It absorbs so much moisture around each particle. So this is the amount. You can see how much is 400, right? Kaolinite has it, but it's not as bad as the swelling type because it's a inert material, so it doesn't have the same moisture attraction. So we went back and looked at soil. You have voids, take out the voids. You have solid particles, sand and silt. They basically don't have the moisture's affinity, so we removed them. In the clays, we took these 3. Again, you may ask me, you have other clay minerals. Why didn't you only consider these 3? These 3 are known as dominating and more stable phase. There are other types of minerals. They are not stable. That's why we didn't include them. So we took these 3, and we came up with a model. Each soil, we can calculate the percentage of kaolinite, illite, montmorillonite, and then I can come up with how much of particles I have in kaolinite, how much I have illite, and then each particle I added the double layer thickness, and then I came up with what is my moisture amount thickness, and then I know the clay particle thickness, so I use this as a calculated amount of moisture that it can surround divided by the particle thickness. Basically, what I did is I took all the particles, their water layer, I added them up, and then divided by the thickness of the soil. That's what is swelling. But if you ask me, that is too high, how do you know each particle is going to get moisture? You're totally right. It's a kind of hypothetical. It gives me the high amount. So the soil that has high amount of montmorillonite is going to give you much larger water thickness. So if I compare it here, if you look here, this is in the hundreds, whereas our numbers are in single to double digit. So, but basically, you can see the trend. The higher these things, you're going to have a higher swelling because you definitely don't have all particles going to be exposed or all particles are aligned to get moisture, but there is a kind of a direct relationship, direct proportional relationship. And we showed it from this research. All our soils nicely fit, and we were able to predict our swell. So this is really fundamental, but again, we showed them this is a simple Excel. All you have to do is 3 chemical measurements. In 2 days, I can get all the numbers. Typically, PIs takes me more than a day also because you have to dry the soil. And this, I know adding extra 1 day, I can get much more meaningful information that I can use to characterize them. Then we want to be a little bit fancy, so we went with some CT, computed tomography, and we try to look at the inside the soil because compacted soils have a different pore structure, how they are connected. So we first looked at the mercury intrusion porosimetry. This is our geosciences lab. So we were able to flush a mercury into the soil. It's a little complicated, but you can put the mercury into the soil. So at different pressures, the amount of mercury passes through. So it'll give me the pore diameter, how much pore diameter versus every pressure you apply. So basically, it gives me the different pore sizes inside your compacted soil. And this one is your tomography. You do it for asphalt. So basically, it will give you the structure. So inside, we can slice it wherever you want, and I can get the how much pores. I can, when the image analysis, you can get that information. So we did this part. So if you look here, this is our pore structure here. So we calculated the amount of pore. So basically, we calculate something called surface area ratio. The way it works is the total pore area, the porosimetry, we can calculate from our mercury intrusion porosimetry measurement, because we can tell in each soil sample, I can tell how much of micropore, macropore, and mesopores. Once I know it, I can estimate the amount of pores. And then if the water is filled in the pores, assuming the soil is fully saturated, the water is only exposes to the surface of the minerals, clay mineral. Only surface is touches, okay? So we calculated the surface area on the top. So we took the surface area of the clay minerals and divided by pore area, and then we got an approximate ratio. And this ratio, we thought it has some relationship. We didn't know it's going to be this good, but we did the surface area ratio, and you can see the swell has a nice relationship with them. And we did at 2 different compaction densities, and both of them actually worked pretty well. And this paper was published actually last year in the ASC journal. Again, this is clearly, if you do a little bit extra work, you can do a better characterization than build something based on simple lab PI test, but then you have a failure, you come back, okay, I missed that soil is too expected. I didn't know it's too, it happens a lot. I believe it or not, at UTA, we get a lot of forensic work. We get a lot of times say, hey, I have this pavement failed in 6 months. Can you go and test it? I had to test it for sulfates. I had to test it for all kinds of things, to see what caused the problem. And I think, if we explain this to our public agencies, DOTs, the importance of this thing, it actually, they can see it's not going to be too time consuming. It is probably a little extra money, but it will help you with your design, okay? So basically these 3 models, we were able to do it, and we have published quite a bit on this, and we have waiting for one more. So it's a fundamental based type of study from NSF. So we are advancing how to characterize soils better. The next thing what we did is a soil stabilization. This project, it came from TechStart and actually worked with another university, UT El Paso, with Sohail. We did this work, which is soil stabilization, but we tried to include a more rational design than using PI, because we know from the experience by having a survey we did with all the districts, what works in one district doesn't work with another district. So if these guys say, okay, I have PI of 25, I can use lime of 6%, and the same guys say, hey, I did the same thing for, I have PI 25, but my soil failed, prematurely failed. So we went back and looked at it. It's because the soils are not same. Again, same reason, expansive soils, and then this is their design. They look at the PIs, they come up with this thing, and then they do the mixed design, and from the mixed design, they include the stabilization. But it's all based on PI, okay? I can show you 2 soils with the same PI, similar PI. They are 2 different materials. One soil may have more swelling, smectite, than other soil. And that means what you are doing, if you have too much of swelling soil like smectite, it won't work in the field. But if you have illite, it works in the field. So the guys in that district has more illite material. They're saying we had no issues. It works very well. But other district has having a lot of problems because their geology of their site soil have more smectite. They both have same PI, but they're totally different animals. So we try to tell them it's not something. So initially when we proposed it, and we are very happy because TechStart chose us, because we actually explained we're going to include some chemical mineralogy. And like some of the times, whether they were asking whether this will be interesting, will it be too practical or too academic? We said it's not too academic. It can be practical because it's going to help your infrastructure. So we convinced them. Again, this is the picture I was talking about, the cracking we have, and this is a thing, this failure of this area. These 2 soils have similar PIs, almost similar, 2931. Look at the dominating mineral. This brand, which is close to College Station, Texas A&M campus here, they have kaolinite. So their soils, their roads are pretty okay. They don't have a lot of undulation. In this area, Fort Worth, where we live in the west side of our campus, we have a lot of montamonite. With the PI is low, but still our soils in this area, if we use the same design, it doesn't work. So we use this as a premise, and then we come up with the durability performance design, and I show you a little bit about this. So what we did is we took the soils from districts in Texas, and then we first identified each soil, what is their mineralogy. These are the three chemical measurements I was mentioning. CEC stands for cation exchange capacity, which is a simple gravimetric step-by-step test. Specific surface area. If you give a soil, I can tell you how much surface you have. And the specific surface, if you have high specific surface, if you have smectite, it's a bad, because your smectite is what you call montimonite, has a high moisture pulling capacity. So it will hold a lot more moisture. So if you put specific surface area and then claim mineralogy, you give me two soils, I'll tell you which soil is better, which soil is not good. Okay, and that's the way we use these two. And this is total potassium. This is the hard test, but we have to use this test because this directly gives a light. From these three measurements, these three unknowns we measured, and we came up with a neural network model, and it actually is Excel-based. We input it. We try to eliminate this because this TP, it requires some kind of hydrofluoric acid, which is not easy to do it in the lab because it requires some special permit. So we try to come up using these two with the dominant mineral, which is montimonite. All I'm interested in is how much percent is montimonite. If I can find it, I can tell you how to improve the stabilization. So using this, then we went back and did the lab testing. So I show you some durability testing. So all the stabilizations were done by TexDot method. Then we did our, in our region, it's wetting and drying. You may do freezing and thawing. But sometimes I feel North Texas, we should do R4, drying, wetting, and freezing and thawing. So that's going to be new durability test. We need to do it. Because believe it or not, we do have some snow days. So we get a lot of freezing too. So each time you soak it and then dry it in the oven and then you measure it. So what we do is different cycles, we go back and measure the strength. And then we try to bring them to the same moisture level at the time of testing. So we get how much strength we have after every cycles, we look at them. And we know initial strength, and we know the strength during the durability. So we know whether we are retaining or we are losing the strength due to this durability. So one reason why we did this, if you have high smectite, you're going to have a lot of cracking, right? So that soil is going to, very easily disintegrate very fast. And that's a good indicator. So I can show you a soil that has a montimonite. If I do it a PI-based design, it's going to disintegrate very fast. And we observed that in our lab testing. I'll show you in a minute. So this is one of the soil, Austin soil. It has a high montimonite. This is, when I say Austin soil, it's a region from Austin collector, from that district they provided. So first thing we did is we went with their design. 6% lime is used. And what you see is untreated soil, after one drying and wetting, it collapses. So untreated, it survived only one cycle. Treated soil, we use 6% lime. It survived up to 12 cycles. So after 12 cycles, the sample failed. Okay, so up to 12 cycles. So we know their design, the TexDot current design is not sufficient. So we tried to increase the lime to 8%. It met 21. It worked fine. And when we tried cement, actually cement gives you higher tensile strength or higher unconfined. So it has a very high cracking resistance, or we call this a shrinkage cracking resistance. So cement actually worked very well. So this is for Austin soil. This is the Fort Worth soils. Again, we have shown it. In some cases, when you have a certain amount of montimonite, even after you increase the lime, it did not work. So lime is not a good test for that. You really need to do performance. You can't just say, okay, all the soils I say PI, high PI, you should go and use only lime. But lime may not work for that soil because you clearly saw, even when we went up to 6 to 8, 14. If I go up to 10, probably it makes it. But most times we limit at around 8%. But we can go a little higher now. Okay, but with this one, cement passed the criteria. So cement is the one we designed differently, and it actually worked well. So when we did all the tests on our soil, all of our soils, and then I'm highlighting some of these materials here, we clearly looked at the trend, how much lime we added, how many times they survived. Our goal is the one that at least meets 21 cycles stable. 21 is just a randomly chosen, it's a long term, but I think a lot of times people use 14 cycles, so we try to go a little bit factor of safety with a high number of cycles. So anytime you have high montimonite, that soil failed, with lime. But if we are below 40% montimonite, it worked. So what we did is in the end, we came up with the design. We showed them if you have a PI less than 35, if you have less than 40, go with the regular design. It doesn't have an issue. because if PI, whenever monoclonal less than 40, it's not too expensive. It works okay. It's perfectly, you will find a good design with lime. But anytime above 40 or high PI soil, we're asking them to do lime increase more. Definitely 8% is not sufficient in some cases. You will have to go to 10 or 12%. So the folks that they do is the PI, in this case is 2930, they use 4 or 5% lime. So they apply, look at the PI, they don't even do mixed design. They directly use the 5% lime. In 5% lime, within 2 or 3 seasonal wetting and drying, we're losing it. The soil is cracking, the first rain is flushing, stabilizer is not holding, so we have a quick loss of our durability, and it's now working. So this is where we mentioned the design has to go beyond, checking the durability testing in the lab and then do it. So we recommended them. And in some cases, we even said you have to probably consider cement. Cement is not a normal approach for soil stabilization in our region, because most times we use lime for expansive soil treatment. But believe it or not, cement actually worked good on very extreme cases because it really provides high unconfined compression strength, which is when the soil wants to dry, this tensile strength will help with the cutting down the cracking. And one thing we learned from this study is a lot of times we do lab testing on swelling. That's easy test because I can compact it, soak it underwater, and do it. If I shrink it, that means if I take a sample, put it in the oven, I get cracks in all directions. If you can show me two same soils, exactly similar shrinking, is very difficult to get it. That's why we don't study the shrinking side. Shrinking side is very difficult to repeatable, is very big issue. It's always an issue with the shrinkage side. So we are now, if you look at it, some of the works coming now in the literature in the swelling soils, shrinkage side is a big focus now. Soils that are shrinking, we are trying to understand how to study them. We have some studies where we are actually doing the same thing, high digital camera to look at the cracking pattern, shrinkage cracking pattern. There's one that is moisture-related cracking. There's one that is structural related. That whenever you have a truckload is going, you are creating a kind of a balance where you have a tensile stresses developing. So all these things can benefit. So in our study, we actually showing fundamentally understanding the constituents, the soil constituents, and then role of them with respect to moisture. Will help you a lot with the design. So this is our recommendation to the TechStart to study for soils that have high amount of them. And we publish these works also in different things. I suggest if you are interested in mineralogy, please look at this paper. With this paper, I was talking to a professor Imad in the morning. He was mentioning Jim Mitchell. Jim Mitchell is my source of inspiration. My advisor is a good friend of Jim Mitchell, Yelchin. So we were doing a lot of soil chemistry, and soil behavior book by him. We still use them. In his book, he actually talked about it. When we developed this thing, Jim Mitchell actually course our work quite well. In fact, some of the sulfate times, whenever someone has sulfate problem, even refers to us. You should talk to Anand. So we are very proud. But he's our source of inspiration for understanding the soil chemistry and how it is. And I can relate this to the fines also. The fines. You always study fines in the basis. The fines and what is the fines are made of, that will tell you how your aggregate base is behaving. If you show me a fine that has more kaolinite base, I don't think there will be an issue. But if you give me a fine that has more montamonite is your source rock material in the ground in the years back when it starts disintegrated, that's the thing that you can contribute to your poor performance of your aggregates. So this is something now actually you see a methyl blue test, which is actually an indicator for montamonite. So that's the way you were now going into this understanding science behind it. So I'm coming to almost to the end, like in the sustainable aspect. So again, as I said, we have to explain the sustainability part of it. In geotech, if I mention, these are some of the areas you may hear. Pavement area is definitely a big one now. But ground improvement, I can say this is where sustainable ground improvement is a big topic here. But most times we do material reuse and recycle, which is our big sustainability part of our work. So as I said, most of the time we come up with material reuse and recycle. Again, this is what we're trying to understand, explain them, how to highlight the sustainable benefit. And the two things is sustainable metrics. I think there's so many ways you can do energy, embodied energy, different types of carbon captures, all the air, NOx, all the different things you can do it. But the one that we would like to highlight in our research is one of them is using novel materials, which I think, sometimes there is a resistance because it's expensive. Why do I have to spend more than yeah, I have issue, but I will repair it every 2 years or 3 years, but then using it. So we tried to explain this one in one of the projects, and we were successful. And then another one is excavated. If you are doing any time pipeline or are we talking about culverts, this is where a lot of materials you're removing it. Are there any way we can reuse them? That's where a huge amount of benefits. And I'll show you one case study where the agency got the high rating because of our research actually. So I'll explain to you in a minute. So I talk about two case studies, geoform and CLSM, which is a controlled low strength material. So in all cases, research is very important. So I don't want research, if you cannot quantify with the CLSM, it's very, with the sustainable benefits, very difficult for us to explain the positives of the research. So in the Geo Institute, ASCE, we have a committee on sustainability, and the international also we have committee on sustainability. We actually explore every area, pavements, I think we worked with the role in the past. How do you quantify the benefits of the sustainability benefits? In fact, next year we got 3 sessions. I don't know whether it's finalized. TRB were asking 3 back-to-back-to-back sessions on sustainability related to pavement geotechniques. So we're trying to get different topics, highlight every area, will explain what are the benefits, what are the things they are doing. So that's going to be next year's January meeting. I hope you all can attend for that one. So let me show you some areas where you see that most of the time is ashes, fly ashes, bottom ashes is very common. Slags, boiler slags, you can use it. Even compost. Compost is a big thing. In Texas, we have a lot of dairy manure compost. We actually try to show them, we can use compost. It gives a natural soil feel. And it also, compost has a lot of what you call is a hydrophilic characteristics. It absorbs moisture from the surface, and sometimes it is 1% moisture or 2%. 1 or 2% is a lot better than having nothing in a summer dry environment, So we showed in one of the area we have a biosolids compost, which is your wastewater treatment plant sludge. We stabilized it. This project came from TxDOT, funded with and local TCEQ, which is the Environmental Quality Regulation Agency, and they funded us. And then we actually did this project. We did a lot of shoulder cracking because the reason what happened is cracks come from pavement shoulders and propagate into the travel lane. If we can cut down in this area, the cracking on these roads will be a lot less. So we demonstrated in this project by each section we have used different amount of compost and mixed it with soil, and then we actually monitor moistures and then also the elevations, and we show compost has a positive, not all compost, but the ones that has a high amount of organic rich material has a very good positive effect. Okay. One question is, what if I'm widening my pavement? Now I'm putting my extra next plane on a soil that has a lot of organic. That's not good. That's true. You can remove them. This is typically top 6 or 8 inches, but we are looking at side shoulders only because that's where the cracks start. Cutting down there is very important for us. Okay. The only area where it didn't work is slopes. We tried to put the compost in the slopes. The rainfall washed away all this because this material is very light, so they all came up. So we did not find compost amendment on the slopes, did not find any positive effect. So we have some cracking. This is not the compost section, but I'm saying we try to use it here. So what we did is we have 5 test sections, control, and this is the compost section. In all of them, these 2 did not perform well as expected. This one did not perform, but this also didn't perform. But these all 3 worked very well for our slope stabilization in cutting down the cracking. Compost did not work very well for our slope stabilization. So let me show you the first case study. This is the one I think Erol has done some work with the railways on the bridge bump issue. We have a 4-year project with TxDOT. We have looked at different materials for embankment, lightweight embankments. So this particular thing I'm focusing is US 67 is outside Fort Worth, State Highway 174. So if I show you, this is the bump. Bump means anytime you have a pro slab reaching your bridge deck, you have a differential settlement. And sometimes if it's 1 inch or even when it crosses 2+ inches, you have to repair it. That's where the bump is. And we have a lot of bridges, a lot of high elevated bridges, 50K, and then 25% of them have maintenance. In 2002, this number is much high. So every time you repair a bump, you have to put urethane or different techniques to raise the slab. That is a very expensive solution. Again, you can see every time you have a repair, you have to shut down forever, again, urban mobility. So we found out a lot of times these are not all bump issue, but the significant of a bump issue in our region actually affects the public perception about the road, and also a lot of repairs. And the one I'm just going to focus is on this one here, US 67. In almost 16 plus years, they have 16 inches settlement. So every year, 1 inch settlement. That high, the embankment in that is around close to 40 feet. The embankment is compressing. And then underneath that embankment, you have a natural subgrade that's also compressing. So almost every inch, like every year you have 1 inch. Whenever 2-3 years, they had to go back and stop it and repair it. So they tried different techniques. None of them actually stopped them. All of them, 2 years, again, the 2 inches came, and then again you had to go back and repair it. So this is the picture of the thing. When we did the thing, we had to show here, this is the amount of settlement, 16.5 inches, okay? And a lot of times what they do is, when we do is we overlay. Overlay is not a good solution. You're adding more weight to the structure. It actually increases settlement. So we looked at some of them, and these are some of the lightweight aggregates. So we were asking them to use expanded. But these are expensive compared to the fill. Fill is like $1 per cubic yard, whereas this is $50, per cubic yard. So that's very expensive, almost 1 to 50. So we did a lot of analysis, and we explained them. Look at the numbers wise. Geofoam has the weight of 0.75 to 2, which is 1/20th. Much smaller than the soils, which is 100 pounds. So we are reducing significantly. It will cut down, but when we do the geofoam, we don't want to do the whole embankment. We only want to do a small 1/3 of the height. The whole height is going to be very expensive. It's not even practical for them. And when we convinced this particular section, which has so much problems, and I had to spend at least 2 or 3 meetings explaining them. I almost became like a salesperson for a geofoam company. I was like doing that kind of thing. So can you imagine a professor going and doing like a marketing? But it's important. Sometimes you have to explain them. So in the end, then you tried so many things, why don't we try? So the area engineer said, yeah, let's go for it, and district engineer bought into it. So we first time built a hybrid embankment. So we didn't take the whole thing. If you look at in the literature, they put geo from bottom up, all the way from bottom to the top of the road, all right? Whereas we did only the, if you look at it, this is here, this is a big embankment down, only top like 10 plus feet we took this thing. So this construction is done 2 days. So all this works, like you can see the 2 people going and cracking. Let me show you these pictures here. So this is basically construction. See the people carrying and then blocking, and you have to put some place shape adjustments, and this is the connection plate, so there's no friction or movement. So we prepared everything. We have closed with the geomembrane on the top. You don't want this material to be exposed to the oil leaking from your trucks, okay? So you have to cover them up. So you need a wrapped system. And then we have, we instrumented this section here. All kinds of pressure cells and inclinometers going from one end. So basically we collected the data. We have been collecting the data even now as we speak. And if you look at it, we have much less, 3+ years now since we constructed it. We have close to around 1.5 inches or less. And most of them came during construction of the placement of these foams. Right after foams, we put the thing, and then we are putting the base on top, and then you have the upper thing. So most of it came, but in the last 3+ years, I'm waiting for the first overlay, probably 5 years or 6 years or even more. They already see big savings, because by now they would have stopped at least more than once to stop it, and they are very happy. And actually, they consider this as the innovative solution. So the TechStart research actually identified this as one of the innovative technology. Again, this is not first time. This is not actually something I did it first. This is a solution that's already there in Europe. They use it for high-speed trains and all other embankment system. Even in US, like if you look at the Salt Lake City Olympics, they did a lot of geofoam embankment systems. So we looked at this literature, and we used this information, and it was proven to be successful. Right now we are monitoring trying to monitor away from the side. We got a new LiDAR system, so we're trying to do everything outside, so we don't have to stop, we don't even have to go close to the traffic. And this actually is working out very well, because we are able to get very fine 3D cloud data. I can use that to get any point I want to measure it. I can tell what the settlements I have. So it's coming out pretty well. This is some of the data that we just showed recently. So this work was pretty successful, and then again, we just have another project coming up, because when a good solution comes, you always get more projects will come, and that's what I wanted to, right? Everybody wants it, right? So we have more research. So the only thing is, the challenging part is the new one is going to be the bridges in the you have a high water table there. So we'll have to see whether that's going to cause any issue. we may have to, because this is floating, this material can float. How do we anchor it so that it will stay? So it's a little bit challenging design, but we're already looking how to design them, and they came up with the geoform solution, not that we have to go and convince them. So we are very happy. We just have to show them how it works. The last case study I'm going to show you is a pipeline. This is, again, it's a little bit from DOT, but this is a major pipeline. We are expecting huge growth in the traffic. I think in Dallas, you have the pipeline bringing water from Lake Palestine and also other lakes here. And then the water is coming to, this is where Dallas. So you have Dallas City here, and then Fort Worth here. The Fort Worth Water District actually doing this kind of thing, and now City of Dallas has joined hands. Okay, so this is where all the water is coming from. And it's a big water pipeline. It's 9 feet diameter, and it's 150-mile length. It's a huge work, several billions of dollars work. So the challenging part is coming on different geological formation. Each color tells you different thing. What you see here is Eagle Ford. If you Google Eagle Ford, it will tell you it's one of the nastiest clay in our region. Okay, Eagle Ford material is known to be highly expansive and pretty. So this area, if you remove this is all buried pipe. It's a lot of places under the ground, 10 feet. So 10 to 15 feet, you remove the soil, you put 9 feet pipe. Where are you going to put this bad expansive soil? Are you going to dump them in landfills? It's going to cost you more. And some of these locations are in small cities, so the roads are not designed for heavy traffic. How do you design them? So we try to show them, can we look at material reuse? Can we look at the excavated materials, and can we reuse them as a fill for the pipe? So we looked at this as a CLSM material. So we remove the soil and then look at it and see whether we can combine them with some stabilizers and prepare them as a controlled low strength material. And it's a flowable, so it will flow around the pipe, and with time it will consolidate and rock. It gives a good support for the pipe. So we know what is required for the properties for pipe, so we use that as our basis, and then we design CLSM material. So the CLSM is typically, again, a controlled low strength material. It requires cement and fly ash and water and native soil. So when we started first time, they mentioned that CLSM is typically fine sand or silts. Mostly clays, particularly CH material, are not used. We know it's going to be challenging because the material should show flow. At the same time, it should get the strength within hours. So one side you are asking the material to, when you put it like this, material should flow nicely. Then when it comes here, you want it to become like a rock. How can you have those two? They're two extreme conditions, right? So we can do with CLSM design. So, but doing with the clay was challenging. So we were looking at different types of additives. So we looked at cement and fly ash. So when we did this project, they want us to do lab design first and then demonstrate in the field. So we were able to do the both. Actually, I'll show you the picture. So in the lab, we came up with the design, and there are a couple of papers in ASC Journal of Materials. I'll show you in a minute. So the challenging part is demonstrating in the field. So when we did this project, and this is the pipe, so we wanted to do here. This is our shredder. We're trying to cut the soil here. The first day was a disaster. When we went there, we tried to cut the clay. This was in summer. The clays become rock in summer. I mean, I'm over saying, but I was stating them. But really, clays, when they're dry, they're almost like a bricks, So shred them is not easy. So these guys are having tough time. But the contractor is very creative. He said, this is not the right shredder. I'm going to bring a new one. The next day, he brought a different one. He was able to cut it into the fine, pulverize them, and then mix everything. And you can see this is the flowable fill it's placing on it. This is the flowable place around the pipe. And it worked very well. And we actually did a lot of non-destructive tests on this. So we did the spectral analysis of shear waves. So we did our guys going down and taking all around the pipe, measuring SASW stiffness measurements. So we show you some of the data. So basically, right after the test, you can see the stiffness is a flow is a wet somewhere over here. Within 7 days, we are in this region here. 28 days, we are pretty high stiffness. So you've got a material that's pretty strong now. So we clearly show how it can really improve the stiffness very quickly. This is, again, for the pipe. You can see all the blue around it. That's what they want to see. So it's working very well. So we showed the calculation. If you reuse it excavated, it costs you $12 per meter calculation. We did a small scale. Carbon footprint is you don't have to bring material from outside, no quarries, no trucks coming and taking. So 0.01 metric ton per meter length. Again, you convert that into kilometers or miles, you can do it. Second one is bringing a quarry outside, which you have to pay, and then you have to landfill. So this is almost a 1 to 7 ratio of savings. So we clearly showed this, and then after we finished this project in a water wall, actually this got Envision rating, silver rating for this one. And this is the rating information, and this is what they identified in that one. They also involved our civil engineering students who evaluated native soils to produce CLS. So actually, it was mentioned. Our research work was cited in their recommendation for the silver rating. We were very happy, and obviously, so again, we showed them sustainability can work. And we can show them with the research. We can go into the from lab, theory, a lab, and field. We can demonstrate in every step. So again, I feel like this area is something is already we know. We are doing quite a bit. So more and more, one issue I will say is the carbon calculators. If you Google it, you'll find a lot of carbon calculators. You do need independent measurements. Some of these carbon calculators, they're developed by not necessarily vetted very well, so you need to double check them. So I would recommend you to look at it. I think this is the one presentation we're going to have next year. EU, they have a research framework that they're developing for hydraulic cements actually. So I'm interested in that one. Hopefully they'll give a talk next year at our TRB. We are looking at their approach, how they're doing the complete sustainable analysis. Their framework is pretty robust in my opinion. So we are using it. Again, I'm part of this ASC Committee on Sustainability. We are worked on this from Geo Institute as one of the members in the past, alternate members for that one. They're doing a lot of Envision. Right now we're working on a book, contributing a little bit in one chapter on the material reuse. So we see there are a lot of things coming. Hopefully it'll go more. So these are some of the papers on the reused material. I think again, any interest, I think, please, this is the paper just came out. I think you all know probably this paper very well, okay? So let me just conclude. Again, the characterization is, in my opinion, simple empirical. What you pay is what you get, right? You do it simple test, yeah, you have a failure, you'll spend more money in repairs or even doing more forensic. So spend a little bit more. I think this probably you heard this several times, but in expansive soil it's very true, okay? Expansive soil, simple lab, it's not always reliable. We have shown and, day after day, like, this is a bad design. Oh, you underestimated swelling potentials. It's very common for us, with this one. So advanced testing is needed, but I think if you put a little bit premium, the testing is much cheaper than repairing and putting forensic work and everything is much. So you please look at that one. Again, I think pavement geotechnic area, a lot of opportunities. If you are getting, please start thinking, how do I get additional 2 or 3 or a one-page section of whatever you have done with respect to sustainability. If you start thinking in that sense, there'll be more and more. And we did a workshop at the Low Volume Road TRB conference. We were a special workshop on sustainability. In the Sunday morning, we thought we may have 20 people. We have 85 plus, from most of them are USDA folks. They do a lot of low volume roads. And we have a topic on geosynthetics on sustainability benefits. Barry Christopher couldn't come, but another person he filled in. So it was pretty well, there are a lot of devotees actually are embracing this idea. It's pretty good to do this thing. Okay, this is something I want to mention in Texas, because we're known for hot summers, but this is really, we have found this snake in one of our inclometer. I have one of my Thai students, actually Thai students they're used to king cobras, right? So this guy is pushing the inclometer. He felt something small, and I think, when he and the 2-3 other students, when he pulled it out, the snake wrapped around our inclometer. I wish I had that picture. But, he jumped 50 feet, it seems. Okay, so I haven't seen, but I was, and then one of my undergrad students took it with the tail and threw it away. And I learned later when I showed this picture, this was a poisonous snake, actually, the way it is. And I told this, don't ever do it, because I don't want to, as a faculty, you are responsible, so we cannot tell them. So, so these are some of our agencies. Again, I want to really thank again Professor Tutumler and Professor Alkazi for giving this opportunity to give a talk to you. And I'll be very happy to answer if any questions you may have. Thank you.
Excellent talk. Questions?
I'm going to ask the basic questions here. We're always confused when we go to the field for the stabilization between the lime and the cement, and you really covered this here nicely and show where it works or where it's not. Can you just go a little deeper into this? What the components of the cement or the lime that is going to interact with the clay that it will make it sometimes work, sometimes it's not. And this is really important now because I guess in many times we are making the wrong decision between the lime and the cement.
That's a great question. In fact, cement and lime actually has similar chemical composition. If you look at it, they both have calcium. So when you react with the soil, with the moisture, what happens is the calcium comes out of these two components, these stabilizers. And then the soil is going to reach pH of high basic environment, around 10 plus, almost like 12. What happens is that a high basic environment, the soils, particularly most of these clay soil, have aluminosilicates. The alumina starts releasing out at high basic. So if you look at alumina decomposition, at around 10 to 12, alumina will come out. So you have alumina, free reactive alumina, and you have calcium, and then you also have silica, because soils are mostly made of silica. So, and then in the presence of water, you get CSH compounds, which is your calcium silicate hydrates, and the calcium aluminate hydrates, and then sometimes you have calcium aluminosilicate hydrates. These are all gels. These are what binds the particle. What happens is, in the case of some clays, if you have high montimonite, these things will form, but high moisture attractiveness will start putting a lot of what you call is a kind of hydration of this material. When they hydrate, they will put pressure on these gels that form, and sometimes the gels will break. They don't show effectiveness. That's why the stabilization within a few seasons starts being ineffective, because the soils that are originally have montimonite, they started swelling. The swelling induced forces are more than the resistance coming from your gels that are formed from the good stabilization. So what happens is the disturbing forces are more than your resisting forces, and that happens when you have a lot of soils made of illite or montimonite. If you have kaolinite illite, it's no issue. The amount of generation of this disturbing forces are much smaller than the stabilization forces from your pozzolanic reaction, so you don't have any kind of destabilization. So it's really the function of your minerals, and that's the minerals and the mineral getting hydrated and how much of disruptive forces are generated in the system, and that happens because about the rainwater, how much it infiltrates. So it's a combination. You may not see the same thing every time, but if you give them time, if you give more water there, you will find the same things happening every time. And that's why when we looked at our durability, when we soaked it and when we dried it, the high amount of disturbing forces coming under fully soaked conditions, if the pozzolanic activity is very strong, this will resist it. If it's not, it's going to fail.
So the key here is the amount of silica that you have difference between the cement and the lime.
Right, exactly. Silica and alumina also, yes.
So in that case, if we go to the fly ash,
yeah,
it's the same.
Fly ash is a pozzolan, so that's a more silica. So it's adding more pozzolanic activity, or enhancing pozzolanic activity. So that could actually provide additional pozzolanic reactions, which will add you more gels in the stabilized soil. So sometimes you can cut down, because cost-wise, fly ash is cheaper than the lime, or lime is almost like cement nowadays. So lime and cement, you can cut it down, by 1 or 2%. Add fly ash. Fly ash, you can actually, they're going to increase price-wise, but then you can add a little bit more fly ash, cut down 2% of lime or cement. That will give you almost similar benefits.
So that's my last comment then. Have you ever tried a combination of the fly ash and lime? Not the fly ash and cement, but the fly ash and lime.
I did cement and fly ash. I didn't do that.
You did, because that's the difference.
Yeah.
I'm saying, because I'm looking at the components and we can get something out of a combination of the two.
Yeah.
So that's why I'm asking you from the chemistry point of view with the soil.
The reason why we didn't do lime and fly ash is because lime was, cement is more expensive than lime. That was the reason. But I don't see why it should work similar way. The lime and cement, almost similar families. They have, if you look at the materials, even though people say lime is more good in clay, cement is more good in sands, it's not. Really, cement, you can use it to stabilize, clay soils also. They have the similar mechanism. Yeah, I think it should work same way. I have not done. I'm pretty sure lime fly ash has been studied by different researchers, and it provides similar benefits. So,
I have a follow-up question, but before moving to that, I just want to mention that keep in mind that with lime and cement, Cement has an additional reaction of hydration, gluing, right? Of course, cement has a higher strength than lime. Most of the time, it becomes more effective than lime, and there is the hydration reaction. They both do pozzolanic. And and whenever you don't have the clay that actually here Nan was talking about, fly ash is a good replacement for clay.
Right.
So that's what happens.
Absolutely. If you have a, yes.
Yeah, coming back to your results on the highly monolithic soils and how actually cement showed higher potential of use, better potential of use. Did you try the lime plus cement? Because often what is happening is just to kill the PI, you go with lime first, and then cement is locks up for long-term strength and durability.
And we actually did City of Arlington. We have actually developed, it's on their website. We use combined lime and cement for them, and it's working very well. Because all they used to do is lime. I was mentioning morning, like our roads now, like local city roads, have 50 years design life. So for that, the lime alone is not going to give enough strength to sustain for that long. So we did combined lime and cement, and exactly using the same thing. Lime is getting benefit because you have to make the soil workable in the beginning. Then you stabilize with the cement. So we have developed a procedure, actually, it's actually a couple of papers on the lime cement information. Yes, we did.
On the durability, instead of doing the wetting, drying, did you do quick tube suction? Is tube suction being used anymore?
They do it at Texas A&M, but we didn't do it. I mean, I did not do it. Tube suction, they have done some Texas projects, but I have never used it. I think that's probably another good test for durability, but this is more standardized test to me.
Tube suction is quite quick, fast compared to a lot of the long time taking freeze tow and wet dry test, especially with cement mix designs nowadays.
Yeah.
So one other thing on the sustainability application you mentioned, which is for the CLSM, control low strength materials. We have been dealing with those quite a bit recently, and I think one thing we found is working with quarry byproduct instead of clay or native soil, which is really tricky to work with.
Quarry fines.
I totally understand how difficult that is. But QBs, I know you work with quarry byproducts quite a bit, sand size often.
That's right.
So isn't that supposed to work a little better with for CLSM use?
Definitely, because that's a quarry fines, but it has a high amount of granular type of fines. Okay. Right. So it works well, because if you look at it, real CLSM is mostly fine sand or silt. Okay, they never use clay. So that's a good product to use for CLSM preparation. Okay, so yeah, definitely quarry fines, particularly coming from a granular type of quarries, you will have an inert fines that is very good for CLSM.
Yeah, I know at the O'Hare Airport, I know they use a lot of the CLSM, especially for drainage, ditches and things like those, just to keep things under control and low cost.
Yeah.
And
we City of Arlington also, where we get sometimes projects, a lot of times they do cut the pipeline leaks. They do it. They always have the CLSMs they use, and those CLMs are mostly made of fine sand and fly ash and cement. They have a truck that mixes there and then pours it there.
Is expansive soil included in a lot of courses down in Texas? Because it's not really taught here.
That's a great question. So actually, the reason why I'm saying is they said expansive soil problem is not a new problem. You have it for last 30 years. The schools in Texas are not doing a good job. Why you have the same problem in roads every year or something? Okay, it's actually there are two things. Two ways I'll answer. These parts we are covering now. Some of them are known. Some of them we are researching as we speak. Okay. In the graduate level, we do cover. Undergraduate level, there's no time to cover any of them. In even lab sections, I want to do sometimes swell design, swell testing. I don't even have one extra class to teach swell. So I end up last day, dead week. I cover on the swelling test because they are local, so they may do this work. So I talk about suction measurements. I talk about swell testing. Just in 1 hour, I just show them some slides and boom, that's it. So I think it's something we had to train it, but traditional curriculum is all built for soft soils, compressible soil, not on expansive soil. But in real practice, a lot of times the problems are coming in areas where we have high expansive soil. Yeah, graduate level, we do have classes. We cover them in the ground improvement course. We spend quite a bit of time on the expansive soil calculation. Then we have unsaturated soils graduate class. which is heavily towards MEPDZ and also slope stability issues. There we covered quite a bit.
One thing I found, agronomy classes, if they're offered, they do a good job in covering the different soil series, soil orders, soil types, like more of a USDA agricultural classification, right? And vertisols are, of course, what we are looking for. So, and how they work, the warp nature of those, the swell, the slicking size, and all those things.
Right.
Some of the lateral pressures you mentioned about actually the undulations, how they form.
Right.
So from that perspective, it's good to connect with the USDA guys.
Absolutely. In fact, a lot of unsaturated soil equipment are all Department of Agriculture. The suction measurement they do, the tensiometers and all, they came from them. So we use their technology. But in my opinion, we took them to one extra level. Now, what they measure is up to 100 kilopascal. Now we can measure up to 10,000 kilopascal, even higher. Under the pavements, summers, we have soils that are going to 3,000 to 5,000 kilopascal, extreme dry. And that can really suck the moisture up, cause all kinds of cracking and everything, So I think, the tensiometers are good initially, but they're not enough to measure what we experience in real field conditions.
Pressure plates would be nice.
Yeah, taking sample in the lab, you can do pressure plate, yep.
One question about the instrumentation you used for that, the slope stability that you did with compost. And what was that moisture sensor that you showed a picture of?
The ones we did is time domain transmissivity. It's a little bit different from TDR. TDR is three-pronged. TDT is like the way it goes and all the way, and then you get chill is a dielectric based. It's a TDT. That actually came from agricultural science folks also.
But that's a non-contact type?
It's a contact. It's placed in the ground.
Okay, but you shoot a camera type of a total camera thing and you put moisture.
That is LiDAR. That's a different one. That's the LiDAR is basically just a deformation type, not going to give moisture information.
Well, I think you wrote that moisture sensor underneath that, so that was complicated.
Which one?
If
Let
you
me
go back to that slide here.
Yeah. Maybe in the ground, probably. I mean. This one?
Or the other one, the one that you had the picture. Yeah, maybe go back.
More, right? Yeah. Oh, you're talking about the slope that has a
Yeah, this one.
Yeah.
That one. What's that on the right side?
Oh, okay. This is total station. Actually, shouldn't be moisture sensor. Actually, underneath this, we put moisture sensor. Okay, this is the wrong one. Yeah, this
so
should be
that's not a moisture sensor.
No, it's not moisture sensor.
Okay.
This should be the same thing. Actually, I don't know. Yeah, the moisture sensor
is the same thing onto the other side.
Other side. Yeah, we copied and pasted it. Thanks for good look.
Yeah,
This is not moisture sensor, guys. Yeah. So all these areas we have moisture sensors placed at two different depths, and with thermocouple, and there are TDT sensors actually. So yeah, thank you. Good eye. He's electronic instrumentation.
Hey, he's a vision guy. Machine vision.
Great vision.
Little something new that we can.
All right. Well, thank you very much. We really appreciate it.